Let's now look at another asymptotic notation called the big O notation, which we will be using quite frequently in this course. So just as I defined the theta notation, I'm going to give an analogous definition for the big O notation. When we say that a function t of n is big O of f of n, what we mean by that is that t of n is bounded from above by a constant multiple of f of n. That is, if we look at the if you look at a plot of t of n versus n, then there will be some threshold value n naught beyond which, let's say this is t of n, beyond which t of n will always be less than or equal to some constant multiple of f of n. So there exists a constant c greater than 0 such that for all n beyond this threshold, t of n is upper bounded by a constant multiple of f of n. So what happens before to the left of this threshold is irrelevant. It doesn't really matter. It's possible that t of n could be less than c times f of n throughout, but it's also possible that t of n starts off being greater than c times f of n, but then it crosses c times f of n crosses t of n at some point. Now if you compare this definition with the definition of the theta notation, or the definition of what we meant by saying t of n is theta of f of n, you'll notice that the only difference in the two definitions is that for the big O notation, we are only talking about the right inequality. So we are only talking about the constant C2 here and the fact that there exists such a constant C2 such that T of n is bounded from above by a constant multiple of f of n. For the theta notation, we had a stronger claim. The stronger claim was that there exist two constants, C1 and C2, such that T of n is bounded from above by C2 times f of n, and it is also bounded from below by C1 times f of n. In the big O notation, we are not talking about any lower bound on T of n. We are only talking about the upper bound. And we are saying that for T of n to be big O of f of n, T of n needs to be bounded from above by a constant multiple of f of n. So naturally, if T of n is theta of f of n, then T of n will also be big O of f of n, because if T of n satisfies this definition, and if T of n is theta of f of n, it's going to satisfy this definition, and so it's automatically going to satisfy the definition of big O of f of n, because the definition of big O of f of n says that there exists some constant such that beyond some threshold value of n, T of n will always be upper bounded by that constant multiple of f of n, and that constant is simply C2. So saying that T of n is theta of f of n implies that T of n is equal to big O of f of n. Again, we have to remember that the equality sign here connotes set membership. It's not a literal equality. So we are saying that this, if you look at this set of functions, theta of f of n, and this set of functions big O of f of n, any function that is a member of this set must also be a member of this set. Right? So if T of n belongs to the set theta of f of n, it must also belong to the set big O of f of n. But an important caveat here is that the converse is not true. So if T of n is big O of f of n, this does not necessarily imply that T of n is big theta of f of n. Because when we are talking about the theta notation, we are talking about the existence of both an upper bound and a lower bound on T of n. So you're saying that there's some constant multiple of f of n acting as the upper bound, and there's another constant multiple of f of n acting as a lower bound. So in some ways, f of n is kind of a tight bound for T of n, because some multiple of f of n is um, binding T of n from above, bounding T of n from above, and another constant multiple of f of n is bounding it from below. Whereas here we are only talking about an upper bound. All that we are saying is there exists a constant multiple of f of n which is bounding T of n from above. This does not imply that some other constant multiple of f of n should necessarily bound T of n from below. So we'll look at this through a few examples in the next few videos.